In this video, we're going to talk about the Poisson distribution, which, in the simplest terms, gives us the probability of a number of events occurring within a certain time. And this is based on an estimation of how many events normally take place within a given time. That might not make too much sense to begin with, but we'll see some examples of what we mean by events later in this video. The Poisson distribution is given by this formula here. It's a probability P, which is given by lambda to the power k multiplied by the exponential e to the power minus lambda divided by k factorial. Now, just as a side note here, in mathematics, this exclamation mark here represents what we call a factorial. And a factorial is the multiplication of all positive integers equal to or less than that number. So what I mean by that, here's an example. 3 factorial, so 3 with an exclamation mark, would be equal to 3 times 2 times 1. And that gives us an answer of 6. Here's another example. 4 factorial would be 4 times 3 times 2 times 1. Every number that's equal to or less than 4 multiplied together. And that gives us a result of 24 in this case. Just while we're on the topic of factorials, here's a couple of slightly more strange or unusual examples. 1 factorial is equal to 1 because there's nothing else to multiply by, it's just 1. But strangely, 0 factorial is equal to 1 as well by definition. And that often catches people out because 0 factorial is not 0. 0 factorial is 1. Anyway, let's get back to the Poisson distribution. Now that we've discussed the factorial, let's have a look at some of these other terms in the Poisson distribution equation here. Lambda, the Greek letter lambda, is the expected number of times an event takes place within a given time period. Now, an event could be all sorts of things. We're going to look at some examples in just a second. And equally, the time period here, it could be a day, it could be a week, it could be a second. That doesn't matter so much as long as we're consistent. And again, we'll see some examples in just a moment. But lambda is basically an indication of how often something happens within a certain time. And this expectation might be based on how often, on average, that event has taken place in the past. Again, we'll see some examples in just a second. And the other term in this equation is k. The formula tells us the probability of k events occurring in that same time period. So let's have an example and see what we mean by all of this. Here's our first example here. A machine shop encounters an average of 3 emergency stoppages per week. What is the probability of there being 4 emergency stoppages next week? So here what we can say is that our time period is a week. We're looking at how many of these events, these emergency stoppages, occur each week. And we're told here that the sort of average number of events that take place each week is 3. So that's our lambda value. Lambda is equal to 3 for this example. But we're asked, what's the probability that there are 4 emergency stoppages next week? So this is the k value, where we're looking for this probability of what happens if there are 4 events that take place. And that's our k value, so k equals 4. So here's our formula again for the probability using the Poisson distribution. And here with our values populated, remember that 4 factorial, in fact that was one of our earlier examples, 4 factorial is equal to 24. And so that gives us a result of 0.168, or otherwise around 16.8% as a percentage there. So again, going back to the question, typically this machine shop has 3 emergency stoppages per week. There's a probability that it could be more, there's a probability that it could be less, but the probability that it's going to be 4 emergency stoppages is going to be roughly 16.8% by this formula. Here's another example. A factory typically has 2 staff absences each day. And there's a few parts to this question. What is the probability of 0 absences, 1 absence, or less than 2 absences? Okay, so again, looking at what we're told here, we're told this typical value of 2 staff absences each day, whether that's an average or something like that. But we're told this kind of typical expectation is 2 absences each day. And so, first of all, our time period is a day. We're taking it by day this time rather than by week. But again, we can just do exactly the same thing. Lambda equals 2 for this example, because we're told that this is the typical expectation. And again, we're going to work out probabilities of when there's 0 absences, 1 absence, or less than 2 absences. So these are going to be dictated by our k values here, because we're going to say that k equals 0 for this first example. So here it is, our formula again. We're going to populate it now. We're looking for the probability of 0 absences. So that's our k term there. And with our values populated, we get a result of 0.135. B, very similar idea for this second part here, but we're going to change our k value here for k equals 1, because we're looking for the probability that there's 1 absence, 1 person absent from this factory here. And so everything else stays the same, but k is now equal to 1. We'll see something like this. Remember that 1 factorial is equal to 1. And just actually, while I remember, going back here to the previous example, remember that 0 factorial is also equal to 1 here when you work this out. Finally, for part C, when the question asks for the probability of less than 2 absences, well, less than 2, it must include the probability of 1 and the probability of 0, because these are only the 2 possibilities that are less than 2. The only things less than 2 are 1 or 0, and we've already worked out these probabilities. So we already know the probability for 0 absences. We already know the probability for 1 absence. And so the answer to this question is just simply a case of adding these probabilities together. So if we can say something like this, the probability of less than 2 must be equal to the probability of 0 and the probability of 1. We know these values, we can add them together to get something like this, 0.406 or 40.6%. So hopefully that video has been helpful as a very, very basic introduction to the Poisson distribution with some simple examples as well.